Hi, this video is about bond energies. We're going to use bond energies to predict whether a reaction is exothermic or endothermic. So we're going to look at how much energy it takes to break bonds, how much energy it takes to form bonds in chemical reactions, and then we'll come up with a delta H value for the reaction. So this is just yet another method to calculate a delta H. So far we've looked at Hess's law by combining reactions and their delta H values. We've looked at heats of formations that we were getting from tables, and now we're looking at bond enthalpies. So first of all, if we're looking at a chemical reaction, so here's a simple one. H2 plus F2 yields 2HF. So we're going to have to break the bonds in the reactant molecules. So we're going to have to break a hydrogen-hydrogen bond and a fluorine-fluorine bond. And breaking bonds always takes energy. And the energy it takes to break these bonds are given in tables in your textbook. And so for whatever particular textbook you have, you can just look in the index under bond energies, and it'll tell you where you can find a table of those values. But breaking bonds always takes energy. It's endothermic. And then on the product side, we're forming bonds, and forming bonds will always release energy, so they're exothermic. And in the case of our balanced equation up here, we are forming an HF bond 2 times because we have 2 molecules of HF. And so to tell if a reaction overall is going to be endothermic or exothermic, you look at how much energy does it take to break the reactant molecules bonds, and then how much energy is given off when you are forming the new bonds. Now remember in the kinetics unit we said that this bond breaking and bond forming, it's all occurring at the top of that hill, or it used to be called the transition state. It's also called the activated complex. But at the very top of that hill, this is where the bonds are breaking and where the bonds are forming. So let's go ahead and look at the enthalpy change of a reaction. There is an equation for this, but it's not given to you on the AP formula sheet, and it's kind of the opposite of what we've been thinking about. So this is just something you need to know, but maybe we can have it make sense for you. So the delta H, or the enthalpy change of a reaction based on bond energies, is equal to, here we go, delta H for a reaction based on bond energies is equal to the sum of the energy of the bonds broken. So and again, that's always going to be a positive value because it takes energy to break bonds minus the sum of the energy of the bonds that are formed. So bonds broken minus bonds formed. Now remember, and I mean, this just kind of makes sense. It takes energy to break bonds. Energy is given off when bonds are formed. So you're looking up the bonds that are broken, and you're looking up those energies, and then when these bonds are formed, it's given off energy, and those values then would be negative. And so this negative sign's really important there because this is exothermic. So let's practice with this. Okay, so I have went ahead and I've looked up these bond enthalpies for this reaction, and here they are. And I'm going to go ahead and write our balanced equation. I always need that balanced equation to look at. H2 and F2, and these are in the gas phase, yields 2HF. Okay, so the delta H of this reaction is going to be equal to the sum of the bonds broken. So we are breaking one hydrogen-hydrogen bond, so 432 kilojoules per mole, plus we're breaking one fluorine-fluorine bond, 154 kilojoules, and we are subtracting from that the energy that is given off, so that's why this is a negative sign, to form 2 hydrogen fluorine bonds. Okay, so when we go ahead and do this, we come up with negative 544 kilojoules. So this is an exothermic reaction, so more energy is released from forming these bonds than was required to break these bonds. So the delta H for this reaction using bond enthalpies is negative 544 kilojoules. All right, let's go ahead and try what I think might be the hardest equation you might be expected to do for something like this. So we have to remember our Lewis structures in bonding here. And let's go ahead and draw this out. So this is methane. CH4 is methane. And so if we draw this out, we have 4 carbon-hydrogen bonds that we're going to have to break. And then we've got 2 chlorine-chlorine bonds. Remember, halogens will never ever double bond. And 2 fluorine bonds. And this 2 here is coming from the coefficient. And then what we are forming is called a chlorofluorocarbon. This is Freon 12. It's used in refrigerants. It's bad for the atmosphere. Carbon is our central atom, and we've got 2 chlorines here, so we're forming 2 chlorine carbon bonds, and we're forming 2 carbon fluorine bonds. We are making 2 hydrogen fluorine bonds, and we're making 2 hydrogen chlorine bonds. Okay, so there is our balanced equation with the Lewis structures drawn. So we've got 4 carbon-hydrogen bonds that need to be broken. So delta H for this reaction is, well, we need to break up those 4 carbon-hydrogen bonds. And so I looked up the bond enthalpy for carbon and hydrogen bonds, and it's 413 kilojoules per mole. And we have 4 of them. And here we're going to put all of our reactants in the bracket. We are breaking 2 chlorine-chlorine bonds, and from a table I get the 478 kilojoules. We are breaking 2 fluorine-fluorine bonds, and that is 308. All right, so the amount of energy it takes to break all of those bonds comes to 2,438 kilojoules. That's how much energy we have to put in to break our reactant bonds. Okay, remember, if we had really, really strong bonds, that would make the activation energy to be high, and the reaction would be slower. All right, what are we doing over here? All right, we have got 2 chlorine carbon bonds. So let's see, chlorine and carbon bonds. The bond energy for that is 678 kilojoules. So we have formed those. That's how much energy is given off for forming those bonds. We've got 2 carbon fluorine bonds that have been formed, and that is, oh, I'm sorry, I had already multiplied by 2 here. This is 339 kilojoules for the carbon chlorine bond, and for the carbon fluorine bond, I'm looking at my table here, it's 485, but we have to multiply by 2 because we're forming 2 of those bonds. We are forming 2 hydrogen fluorine bonds, and that is 565. And I'm going to have to go below here. And we're forming 2 hydrogen chlorine bonds, and that is 427. So here is the energy that is released when we form the carbon chlorine bonds. We do that 2 times. 2 carbon fluorine bonds. There's the bond energy taken from a table. 2 hydrogen fluorine bonds and 2 hydrogen chlorine bonds. And when I do all of this here in this set of brackets, so the amount of energy released when those bonds are formed, I get 3,632 kilojoules. So we can see that more energy is given off in the formation of our products than is required to break our reactant bonds. So this is going to be an exothermic reaction because more energy is released. And so now we just have to do our simple subtraction here. And we are going to get, let's see, I didn't mean to do that. We are going to get a negative 1194. Again, another exothermic reaction. So there we have it. That's how we use bond energies to calculate the enthalpy of a reaction. It's not an equation that's given to you, but it should kind of just make sense. It's the sum of all the bonds you have to break, and then we put a negative sign in because you then go and you calculate the sum of all the bonds that are formed, and that releases energy, and that's why there's that negative sign there. So we're going to practice this a little bit, and I hope you remember a little bit about Lewis structures, and we'll see you soon.